Hi, everyone. Sounds good? Okay. Thank you very much to the organizers for inviting me, and many apologies for oversleeping this morning. Yeah, I had my noise-canceling headphones on and also an alarm, it turns out. This combination is not so good. Anyway, it's got to be a first for me. So this is my first time in Lumini. I'm very happy to be here. I like the weather very much. This is like fall-time weather in Michigan. So as a comparison, I looked up what temperature it is in Michigan, and it was minus 16 Celsius. So anyway, I'm very happy to be here, and even with short sleeves. Okay, so yes, so as Olivier said, I will give 4 talks. So this first talk will be basically completely expository on classical material. So I'm sure for some of you, this will be just super basic stuff that you learned as a student many years ago. But I'd still like to start there. And so even more basic, I'd like to start with a picture that I think probably all of us saw as undergraduates, maybe. And so ultimately, what's driving a lot of my research interest is representations of p-adic groups. And so let me set up some notation for this. So I think for all of my talks, F will be a non-Archimedean local field. And so this means something like the field of Laurent series over FQ, or it means a finite extension of QP. And the structure of this is very nice. So inside F, one has the ring of integers. So ring of integers. And inside the ring of integers, the ring of integers is a very simple ring. There's a unique maximal ideal. So let me choose a generator of it. So that's called a uniformizer. So where do I want to write it? Maybe I just like this. And so when you quotient this by the ideal generated by this uniformizer, you get a finite field. And I'll call this FQ. So this is my finite field. Okay, so this is a familiar picture. And kind of the difference between OF and F is very minor. It's just powers of the uniformizer. But of course, the difference between these two is kind of big, right? This is kind of like a bunch of FQs in layers. And so, okay, so this is like this. So now, if I am given, say, G, a connected reductive group, defined over something like sufficiently general to make the following picture work, well, I can write down, so you should think of G as something like GLN, or GL2, as I will often specialize to in today's talk, is that inside something like GL2 of F, I have GL2 of OF. And this has a natural quotient map to GL2 OF mod this thing. So this thing is now G of FQ. Okay, now I realize I messed up the spacing on this, but okay, so whatever. Okay, so something that one often does as a starting point to study representations of this group over here is to start with representations of this finite group, pull back to get representations of this not finite group anymore, and then compactly induce to get representations of the original p-adic group that you're interested in. And so this is a strategy that began, I don't know, some number of decades ago, and it yields very interesting representations over here. This kind of story at this level we call depth zero. And the reason, and if there's a notion called depth, then you imagine that there are other things that depth could be. And what is that? Well, the analog is kind of what I already said a little bit before, which is, of course, I can quotient this ring by the maximal ideal, but I can also quotient by powers of it to see more of the ring, right? So instead, I could have gone to OF mod pi f squared, or in general, OF mod pi f r plus 1. So the reason for r plus 1 is that this thing that I call depth 0 should be r is equal to 0. Okay. And so one can imagine that that it's reasonable to consider the analogous picture in this p-adic group situation, is that if I want to try to understand some part of the representation theory of G of F, which is not just coming from the depth 0 part, I should also consider not only the representations here that came from this very small group, but things where I'm allowed to feed in these finite rings. Okay. Okay. So maybe I'll write, this is representations of p-adic groups. The general representation theory over here, I think, is very difficult to understand, more difficult than understanding these. And so in the story that I will tell over the next few lectures, I will mainly focus on the representation theory here that gives you enough to understand the representation theory over here. And oftentimes we call these kinds of things, not all the representations here, but some special ones here, types. I'm using this a little bit loosely, but yeah. Okay. So what I'd like to explain a bit is some developments in understanding the picture on this side, and therefore the picture on this side in geometric terms. And so let me say a bit what I mean by geometric terms. Is that going to damage this? Too late? Okay. We can test. I have more power. Okay, so I think maybe the title of this week is called Geometric Representation Theory Around the Langlands Program, something like this. And geometric representation theory means many things. So let me be clear about what I mean in these lectures. So geometry. Let me say geometric representation theory for me in these lectures means one of the following two things, and these two things I often think of as in parallel. So the first is the following. So say I have X, a variety over FQ or FQ bar, whatever you like. Maybe I say over FQ, but when you take cohomology, you could do it over FQ bar anyway. So, so say this is a variety with an action. I think I don't want, let's just say like this. An action of some group, and the group that I will often take is G of FQ or any of the finite groups on the right. But let me write this down for G of FQ. Then from this variety, I can consider its étale cohomology. And this now gives me vector spaces over QL bar, which I will just identify with C in your favorite chosen way. This thing is a vector space with an action by G of FQ because by functoriality of cohomology. And so this is one way in which a representation of G of FQ can arise geometrically. It arises by appearing inside the cohomology of some variety that I gave you. So typically, the individual cohomology groups are quite difficult to study, and so it's much easier to understand the Euler characteristic. And so that's what I'll say over here. Often, maybe always, we'll only study the alternating sum. Considered as a virtual representation of G of FQ. Okay. So this is one way in which one of these parallel pictures. Let me indicate the second one. So now suppose that instead I focus on G, which is this thing defined over FQ. So say F is an object in the derived category. So say like, okay, it's represented by a complex of constructible QL bar sheaves. Oh yeah, so this is QL bar sheaves. And assume that it's on G where G is defined over FQ. And so what that means is that in particular, I have some Frobenius equivariance on this object. Then there's a mechanism, there's a dictionary between these kind of fancy objects and just functions given by something called the sheaf to function dictionary, which I will briefly review here. Then F has an associated function. And I didn't write this in the notes, but maybe I will give this function a name. Maybe I'll write, this is a big theta. Yeah, do I want to do this? Yeah, well, the choice is big theta or chi. Do you have a preference? Okay, is this okay? Okay. Oops. And this is given by, if I take an FQ point, then there's the associated geometric Frobenius acts on the stalk of this F here, and so that means that I can take its trace, and that's what this says. The Frob at G, and you act on the stalk of G. And if, moreover, your F is not just in this, but has an additional structure, so maybe that wasn't quite the right way to say it, because there are some subtleties in defining equivariant derived categories. But if I sneak in a G here over here, then this associated function has an additional structure, and that additional structure is its invariant under a G of F conjugation. i.e. it's a class function. And everybody in representation theory loves class functions, because class functions are what you get when you take a representation and you take its trace. And so these two parallel pictures, I mean, they're in parallel, but they're not quite geometrizing in the same way, right? In this situation, the representation is arising from geometry, and in this situation, only its character is arising in geometry. Okay, and so my goal for today is just to explain the beginnings of these two pictures in the setting that you have a connected reductive group over FQ. So this is the setting of finite groups of Lie type. So maybe I'll say it like this. So today, which is talk number 1, explain a bit of this. For G connective reductive over FQ. Then tomorrow, I'll set more alarms tomorrow. I'll explain again a bit of this for these groups farther down the list. And those groups farther down the list, I actually should have written this, but those groups can also be realized as the FQ points of some algebraic group, but that algebraic group is no longer reductive. How to write that? So I'll write it in the way that for GR, where GR is, I will say what this is tomorrow, the Arth-Jet scheme of G, where G is connective reductive over FQ. Talk number 2 actually works in more generality than just this setting, but I find that this is an easy way to exposit this subject. In talk number 3, I will talk about something called, that I like to call isomorphisms on sale. And let me say briefly what this says a bit. So in this picture over here, we have this representation theory geometrically that we're trying to study on the right-hand side, and we want to relate it to representations of p-adic groups. But there are very interesting things that happen when comparing these pictures. And so the point of this talk is to explain one technique where you can conclude that two representations are isomorphic just by knowing the character formulas on a very small locus. And so I call it on sale because you're getting a nice conclusion, isomorphism, for a heavily discounted price. You only need to pay a small amount of the character. This will be very fun, and I think it's good for Wednesday. And then in talk number 4, I will give some proofs of some of the things that I will talk about in talk 2. Okay, great. Okay. So I think I tested this earlier. You can't do this for multiple boards simultaneously, so we'll just do one at a time. Oh, but maybe it's reasonable to just do this one, okay. Okay. Okay, so what? Yes, I was told that, and yes, I thought about it, but I didn't have the brain power to figure out what to put on the sideboards. So yeah, thank you. Okay. So for G connective reductive group, oh, actually before I say this, so the first bullet point is in this setting is due to Deligne and Lusztig in a very famous and incredible paper in 1976. And the second one is due to a series of very incredible papers by Lusztig developed in the 1980s. Okay, so I will talk about Deligne-Lusztig theory. Okay, I received a suggestion to use the sideboard. Let me use the sideboard. Okay. For just this one thing. So here's something to keep in mind is, and maybe this is, okay, so this is technically wrong, but if I want to study something like EREPs of a complex Lie group, let's say finite dimensional, these are parametrized by W orbits. This is the Weil group of regular, for some notion of regular being far from trivial characters of T of C. And you could ask, okay, well, can you do this same thing where you replace C with other things? Maybe you want to replace it with R. Or maybe you want to replace it with our context. Or maybe you want to replace it with the context we started with before I erased, which is the setting of p-adic groups. This is like this. And kind of the farther down you go this list, the more false this is. But you can still kind of maybe, so star means not quite, but you can use this as a guidepost for at least getting some proportion of the representations. And so, and this will be a common theme that arises throughout these talks, is that I'm trying to get at the representations over here by first giving some constructions that allow me to input some information from the torus. And so with that, let me start Deligne-Lusztig theory. So Deligne-Lusztig theory. Okay. So again, I start with G, a connected reductive group over FQ. Part of this theory is a bit easier if I allow myself that this is a connective. I kind of separate the FQ-ness. So I'm going to take this over FQ bar, and to remember the FQ rational structure, I will record Frobenius. And so if I write G of FQ, I'm meaning G of FQ bar, the sigma fixed points of this. And now I take T inside G to be a maximal torus. And so this means that T is a product of GMs. And we'll always assume that T is F stable, or a sigma stable. Okay, so we have this. Okay, so I'd like to give a basic example that probably, again, many of you in this room have seen before, probably many times, but I still want to give it. Say we have, let me do this actually. Oh, actually, this one kind of interesting to leave up. Whatever. Okay. Okay. Okay, so for GL2. One thing I can take is, I can take T to be GM times GM, shoved inside GL2 as the diagonals. This is a maximal torus of GL2. And one Frobenius that I can take on this is the one where I simply take A, B, C, D and map it to A to the Q, B to the Q, C to the Q, D to the Q. That's something that I can do. And obviously this image is sigma stable. But the other thing that I can do is the following thing. Again, GL2. And again, okay. Let me say this. Continue this over here. What is T of FQ then? This is very easy. This is just isomorphic to FQ star times FQ star. Okay. So I again take G equals to GL2, and I again take T to be GM. I mean, there's no choice. It's always isomorphic to GM times GM. And actually, I'll take the embedding to be the same as well. But now I'll take a funny Frobenius, a twisted Frobenius, which I'll call sigma prime. And sigma prime will be defined to be like this. I'll see what it is. A to the Q, C to the Q, B to the Q. And this thing is simply this element multiplied by sigma of A, B, C, D. So that's why I call it twisted Frobenius, because it's being twisted by this W, this element of the Weil group. And in here, you can compute what this is very explicitly. And this thing I mean, you can see this is also, the image is also stable under this thing because it's just going to swap it. And the condition is that A is equal to D to the Q, which is equal to A to the Q squared. And so this thing is isomorphic to FQ squared star. Okay, so I have these are two different tori inside GL2. They're different, I mean, their FQ points don't even have the same size, right? This is Q minus 1 squared, and this is Q squared minus 1. And in this picture, we kind of see the first way where this row might be more interesting than this top row, which is that in this complex thing, there's only one torus, but in this finite field setting, I have multiple tori. And there's a very nice general picture about that. They're indexed by conjugacy classes inside the Weil group, which in this case is just Z mod 2, and so I get these two. Okay, and so I mean, there's a very natural reason why there are more tori over here than over here, and basically it's a linear algebra reason. If you have a complex matrix, the eigenvalues are complex, but if you have an FQ matrix, the eigenvalues might not be in FQ, right? Your characteristic polynomial may have roots in some field extension, and that's the difference between these two settings here. Okay, so the point of Deligne-Lusztig theory is to provide the idea here, or maybe the end goal, is this provides a kind of mostly bijective. So mostly is why there's two stars over there. Map between pairs given by a maximal torus and a character of the FQ points. So here, T inside G is a maximal torus. And theta is just a character, a group homomorphism to C star. From here to the irreducible representations of FQ. Okay. Oh, okay. So I said W orbits, and I need to cover the W orbits over here. And so I quotient by the action of W. There's a rationality thing over here. So this W is rational one. So this simply means all things in G of FQ for which NT and inverse is equal to T. Okay. So this is the end goal. Okay. So in order to achieve this end goal, let me explain what this picture, this map looks like in this GL2 setting. Yes, you are right. Right, so I want to quotient it before I vary T. I see that I have not written it in this way. It's so far away. Okay, so when it comes back down, I will modify it. Okay. Yeah, so for each T, I mean, right. So basically for each T theta, I can, instead of just considering the one pair T theta, I consider it's a WT orbit. And so each of those I place as one object on the left-hand side. Okay. Okay. Okay, so let's continue with this GL2 example. And then after that, I will give you the general definition or general construction of this. So on this left-hand side, what I can do is I can consider the upper triangular matrices. And so in my number, oh, I see, okay. Well, the letters are a bit funny, but like, right, because I should have written A and D for T, but okay, everyone can deal with this. So I take B is for Borel. The upper triangular matrices, this thing is stable under sigma because sigma just raises everything to the qth power. Okay, and then inside here, I also take U to be its unipotent radical, which looks like this in this case. Then what we have is not only does T live inside here, but actually T also appears as a quotient of this. Okay, there was a smarter way to write this down. But now we have this like funny, like my secret is this. Okay, whatever. Okay. Okay, so what is my goal? My goal is to start with a character of the FQ points of this thing and end up with a representation of GL to FQ. What I can do is pull back along this map so that I now get to start with a bigger subgroup and then induce from there. So, I mean, you could choose not to do this and just induce from here, but just no matter what you take in that setting, it won't be irreducible. So the idea here is try to expand to as big a group as you can and then hope that the induction is irreducible. So for any character here, one can consider its associated parabolic induction. And so here's the definition of parabolic induction. It's simply given as the induction from B of FQ to G of FQ, where G is GLN. But I mean, I write this in this way because it really doesn't depend on it being GL2. And this is a space of functions. The space of functions, it's the space of all functions on G of F, which transform in this way under the right action of B. And so this is equals to theta of pra of B times F of G, and then for all G in G and for all B in B. Okay. But of course, okay, so this map here was pra here. So of course, what this means in particular is that if I actually started out with something inside U, then, and I multiply on the right by U, then this thing is going to be trivial. And so I just get F of GU is equal to F of G. And so I have right invariance by U of FQ. So instead of thinking about it this way, one might think about it as the space of functions on the quotient, like this, such that F of GT now, G is now coset of this. GT is equal to theta of T, F of G, again for all G and all T. So what does this say? This says here, move this up slightly. This is a space of functions, G of FQ, quotient by U of FQ, where the torus part is acting by some theta. And so I'll write it in this way. Okay. Okay, so oopsies, let's not. Okay, so it's easy to compute. So actually, this defines parabolic induction, but I will also have this define RTG theta in this setting that of this sigma, not the sigma prime, but the sigma. So one thing that's easy to compute is the irreducibility behavior of this representation over here. And this is a very easy computation. So if you take two characters, theta and theta prime, of this T of FQ, then the Hom space between RTG theta and RTG theta prime is equal to one of the following two things. It's equal to 0 if, oh wait, okay. How should I say this? Okay. Okay, I realized there was a computational error in my thing. So now I have to think on the spot. So the numbers are 2, 1, or 0. And so it's going to be 2 if theta is equal to theta prime, and also theta of AB is equal to theta of BA for all A and B. Okay. It's going to be equal to 1 if theta AB is not equal to theta of BA for some A and B, and either theta of AB is equal to theta prime of AB for all AB, or theta of AB is equal to theta prime of BA for all AB. And then it's equal to 0 otherwise. Okay, so if you unpack this very explicit description, a simpler way to say this is that this dimension is equal to the number of ways that you can get from theta to theta prime using the rational Weyl group. Okay, so in particular, I'd like to point out that if you take theta and theta prime to be the same, then this gives you a criteria for when this representation is irreducible. It's going to be irreducible exactly when you're in this middle case, which is that you're in a situation that theta of AB is not quite theta of BA for some A and B. Okay. Okay, so I won't write that down, but I'll just leave that here for now. Okay. So this takes care of this left-hand case, which is the easy case. I mean, how you should come away from this is some easy process just from classical induction, and you can compute everything explicitly here. So what happens on the second side? In the second case, it's a little bit more interesting. And so let me describe it. Okay, I also realized I want to call this embedding, like the image, I'm kind of identifying T with its image here. I'm going to want to put T prime for both of these so that it's clear that they are different. Okay. Okay, so example again. What about T prime? What do you do there? Recall here that we had the sigma prime, which is a little bit different. And if you try to do the same thing as before, what you'll find is that you get stuck when you write down B of FQ. You cannot write down B of FQ because sigma of B is not B anymore. If you apply sigma to B, you get the lower triangular thing. And so this very nice parabolic induction doesn't work here. And so we have to do something a little creative. And so here's the creative thing that you can do. So this was defined by Drinfeld when he was like 16. you consider the following thing, which is the affine curve given by x to the q plus 1 minus y to the q plus 1 to the q minus 1 is equal to 1. This thing is called the Drinfeld curve. If you've seen this before, then maybe you might be more happy with xy to the q minus x to the qy all to the q minus 1 is equal to 1. They're isomorphic over fq squared. And the difference between that one and this one here is that I want the one that's associated to this sigma prime rather than kind of some other renormalization. And so, okay, so what did I promise in the thing with 2 bullet points is that if I give you a variety and I have group actions on it, then I can take its cohomology that gives me representations. And then if even better, I have actions by 2 groups, G and T, then I can use T representations to get G representations. So let me say how that works over here. So over here, I can take G of FQ. This G of FQ looks a bit funny because of this, this funny sigma prime, but it is still isomorphic to GL2 FQ. Nice exercise if you like to do it. And then the other thing that I can do, I just act by matrix multiplication on x, y, that vector. And then over here, I can act by T prime of FQ, which remember was isomorphic to FQ squared star. And I can act by just scaling x and y simultaneously by some scalar inside FQ squared star, right? And that's clear, that's an action, right? I plot an alpha to the q plus 1, alpha to the q plus 1, that pulls out to alpha q plus 1 times q minus 1, which is 1. Okay. So what's also clear is because this is by scaling and this is by matrix multiplication, obviously these 2 actions commute, right? And so I'm in a situation that not only my x has an action of g, but it has an action of g times t prime. And so that means that then the cohomology has an action by g times t prime. Okay, and so we can do the same kind of definition as up here for parabolic induction, but now slightly fancy. For any theta character of this FQ squared star, we can consider what's called its Deligne-Lusztig induction, RT prime G theta, given by the Euler characteristic, thought of as a virtual representation, X, I called this X. And then I put this theta here. And what does this theta mean is that, as I explained verbally, without this theta, this thing is a representation of G times T prime. And so given any character of T prime, I can consider the subspace on which T prime acts by theta. And that then isolates for me some, turns out, interesting representation of G, and that's what I call RTG theta. So this is some way for me to get from T representations to G representations. Okay. Yes. No. Okay. Say again. Theta on the top? Like up here? I don't know, like somehow this is how everyone, right? You prefer on, why do you, oh, because it's like, I see. Because it's like, if theta was trivial, then it's like the invariance. That's what you, I see. Yes, somehow it's more common to write it down here. Okay, so it's much harder to show what the analogous statement over here is, but in fact one can, but one has something very beautiful. So it's much harder to show. And I think I'll actually give some outline of what the proof looks like tomorrow. But in fact, one still has that RT prime G theta, RT prime G theta prime. So now theta and theta prime are characters of this T prime of FQ, not the one over there. This also has 2, 1, or 0. And the condition here is going to be 2 if theta is equal to theta prime and theta is equal to theta to the q. It's going to be 1 if theta is not equal to theta to the q, but theta prime is 1 of theta or theta to the q. And it's going to be 0 otherwise. Okay. And again, this has the very nice, simpler phrasing that this is simply equal to the number of things in the rational Weil group for this T prime where these two things are the same. Okay, I should say that a comment here is that in this particular case, this group is actually equal to that group. But in general, that's not the case. Like if you take even one bigger, GL3, the analogous thing over here, which is a split thing, the Weil group will be S3. But over here, when you do this for the non-split torus, it will actually be Z mod 3, so much smaller. So just something to keep in mind. Okay. Okay, so let me now give the general definition.
When the neighbors can apply both the condition for 2 and the condition for 1.
What? When what?
The condition for 2 says that it was applying both.
Yes.
So if it doesn't equal to the Q, but that it was applying with a condition for 2 hard as well as the condition for 1, then I might be missing something.
You're saying that you're saying that these two aren't excluding each other? Is that what you're? Huh? What? Wait, okay. So this one. And? Yes, this is an and. Oh, I see. Oh, I see. Okay, great. Okay. Okay. This is a universal symbol. Okay. Sorry. Oh. Okay. Okay, so what's the general definition? General definition is I take T inside G to be a sigma stable maximal torus. So both sigma, as in my example, sigma and sigma prime are both allowed. Choose a Borel B containing T, let U be the unipotent radical of B. B and U are not required to be sigma stable. Okay, then the associated Deligne-Lusztig variety to this data is, actually it also depends on B, but I'm going to suppress that since this is supposed to be a kind of introduction to what the shape looks like, not all the things that can go wrong. And I simply take all things where sigma, G inverse sigma of G are inside U. This is called the Lang map here. So it's just a pre-image of the Lang map of U here. And the corresponding Deligne-Lusztig, so this is the Deligne-Lusztig variety. And what we call Deligne-Lusztig induction is RTG theta, is RTG, which says the following thing, is that given any theta, which is a character of T of FQ, then I define this to be the virtual representation given by this thing here. Okay, so this is the definition. It is not hard, and I encourage you to do it, to see that if I take in this example and I specialize it to the case of GL2 for sigma and sigma prime, then in the case of sigma for the split situation, I will get not quite G of FQ mod U of FQ, but something that has the same cohomology of it, and the cohomology will be simple, it'll just be the space of functions. And in the second case, you can really compute that this thing gives you the Drinfeld curve. Okay. Okay, so let me define something, a term that I will use very often is we say that theta in T of FQ to C star is regular. Classically, this is more commonly written as in general position, but I will use the word regular. If the stabilizer of this character under the action of the rational Weil group is trivial. Okay. And so this is a setting where this map here, at least even if it's not, like even this, if this isn't bijective, this correspondence is like at least its restriction to some part of it will give you a irreducible on the right hand side. And so that's why I specialize to this. And here's, I now want to write two important theorems. The first one is a generalization of this kind of RTG paired with RTG, which is called the scalar product formula, which is that if I take T and T prime to be any two sigma stable maximal tori, and theta prime to be characters of T of FQ and T prime of FQ, then it is always true that RTG theta paired with RT prime G theta prime is equal to the number of things. Now, I didn't do it this way, but there is a way to kind of put both T and T prime in the same sentence. I would just change the embedding from AB goes to the diagonals to something a little bit twisted. And so this T and T prime really might not be the same. And so I won't be able to get from theta to theta prime just by the Weil group. I need to take the, what do you call it, like transporter or something like that. So all rational ways to get from T to T prime, there could be none. So all W inside here, for which theta W is equal to theta prime. So, okay. Okay, so there is something called the Deligne-Lusztig fixed point formula that's extremely important and goes into the proof of very many things. And I will describe this tomorrow. So what I'd like to do next is now the second bullet point. So this is my beginnings on Deligne-Lusztig theory for connected reductive groups over finite fields. And next I will describe character sheaves over these objects. Okay? Oh, yeah, I want to say maybe one last thing, since I did define what it means to be regular, is that in particular here, RTG theta is irreducible if, and in fact, if and only if, theta is regular. Okay. So the regular picture will play a very large role in these lectures. Okay, and now we switch gears to this other kind of way of geometrizing. And so the starting point of character sheaves is something called the Grothendieck-Springer resolution. And if you've seen this before, you'll know that there are many ways that it's a natural thing to write down, and I will describe why it's natural to write down from like a very basic representation theory perspective. So here is the definition of the Grothendieck-Springer resolution. Okay. And it's the following thing. I take G tilde to be defined to be, okay, so here G is now over FQ bar. I take G tilde to be all pairs, G comma HB, and again, B is the same kind of B that I have been having, such that H inverse GH is in B. Okay, define this. This has two natural maps. It has a natural map to T given by, I take these two things. I know that H inverse GH is inside B, and so I can get to something inside T by mapping down to T from B. So I take the projection onto T of H inverse GH. Okay, so there is something to check here, which is that this projection didn't depend on the coset representative over here. But whereas if I just went to B, then it's not actually going to be, it's like going to conjugacy classes of B. But, okay, and then there's another map to G just given by projecting onto the first coordinate. So there are various standard terminology ways to write these two maps. I will call them pi and f. Okay, so let me define now geometric parabolic induction. And I'll call a parabolic induction from T to G of some sheaf L. So I kind of, okay, well, yeah, so I start with some sheaf L on my T. And actually, I think everything I'll say, I'll only care about certain sheaves here. I think I'll only care about local systems, which have the additional property that they're multiplicative, which means that if you pull back L under the multiplication map from T times G to T, you just get L, like a box times L. And so if this is not an object that you've seen before, I want you to think of this object as being the analog of a one-dimensional representation in the previous discussion. So this L now is replacing the theta, and I will say in a moment in what way this is. Okay, so this is defined to be this thing here. Okay, so all my push forwards are derived from push forwards. Okay, so what I'd like to start with is the motivation to why you might consider this kind of object. In the same, okay, yeah. Okay, why should you call this parabolic induction if you haven't seen this before? So say I'm in this kind of nice situation like the sigma for GL2 and not the sigma prime of GL2. So this is a situation where I have my G and my T, but also my B is sigma stable. Then this sheaf to function dictionary that I described at some point earlier has many natural properties, like kind of natural things that you do on the geometric side correspond to natural things that you might do to a function. And so some very easy thing that you can observe is that if you pull back on the geometric side, this should correspond to pull back on the function side. Something that uses a little bit more, like you use a maybe Grothendieck trace formula or fixed point formula to show, is that if you do a push forward, then this corresponds to some averaging process. And so over here, I have a pullback and a push forward. On the function side, I should see a pullback followed by an average. And so in this situation, if I take if I take this kind of L and I take its trace of Frobenius, its corresponding thing will be, because of this multiplicativity property, will in fact be just a group homomorphism from T of FQ to C star. So this is the sense in which I think you should replace this L as like recorded in your head as this is the local system. This is the sheafy version of my theta. And so you should ask, okay, well, from this, can I compute what this here should be? And this is not hard. This corresponds to the following thing. So I have to do a pullback. I pull back my function and I get this over here. And what do I do? Like, where are these h's? These h's are living over, these are the rational points lying above G. So I'm taking an average over all of these. And so that means that I'm taking all h B of FQ sitting inside G of FQ divided by B of FQ such that H inverse GH is in B of FQ. But this is a very beautiful and recognizable formula. This is simply the character of the classical induction from B of FQ to G of FQ of this theta here. So it's very natural to call this thing a geometric parabolic induction. In this case, where everything is as nice as possible, it is simply giving you the same function under the sheaf to function dictionary as just the trace of parabolic induction. Okay. So now, given the structure of this, the way I've set it up, I think the natural question is, well, what happens if in my GL2 case, I want to work with T prime and not just with T? Then what is this geometric parabolic induction giving me? And to describe this takes a little more work, as one would expect, because for T prime, it did involve a little more work up there as well. Right? And so let me describe what this looks like. Yeah, okay. So what I can do is I can consider inside here, do I have enough space here? Maybe I have enough space here. I can consider inside here the regular semi-simple locus inside G. So in the setting of GL2, for example, all this means is that you take the matrices that have distinct eigenvalues. That's what regular semi-simple means. And what I can do is to say, okay, I look at the Grothendieck-Springer resolution, but I only look at the part above this regular semi-simple locus. This thing is open and dense in here, in the same way that like 100% of matrices have distinct eigenvalues. So what does this look like? Well, this thing in the middle here actually has an, I guess the pre-image under this pi inverse of GRSS. Okay, so let's first, of course, okay, well, this goes to TRSS sitting inside here. Pi inverse of GRSS has another description. This thing is, in fact, also the same as a set of all pairs G comma HT, such that H inverse GH is inside T. So that means that by restricting to the regular semi-simple locus, I've removed B from the picture. I can do everything in terms of T, nothing dependent on B now. Okay. And so this means that if I'm in a situation where the sigma of B is not equal to B, well, I may not be able to do this thing up here, at least sigma rationally, but down here I can definitely do everything and it didn't matter. So, so I guess what I mean is we can always form I guess we can always form the top thing, just not like sigma rationally. We can always form this new one over here, pi RSS plus F RSS. And if I have an L over here, I'll call its restriction L RSS. I can always form pi RSS push forward F RSS. And moreover, if my LRSS had some nice sigma action, then this whole thing also has a nice sigma action. And that's not at all clear from up here because sigma might move the B to somewhere else. But sigma is not moving anything to anywhere else in this lower picture over here. And then also, once I have something like that, of course I want to get back up to G. I can do this by using this machinery called intermediate extension. And if L had sigma equivariance, then so must this thing here. Okay. So that means that we now need a theorem to get from this thing back to the original parabolic induction. And we have such a theorem, thanks to Lusztig, which I will write down now. Okay, so I take L to be, as usual, a multiplicative local system. The theorem says, actually, I don't think you need it to be multiplicative for this theorem to hold, but LRSS. And this is simple. If and only if L is regular. And I don't want to write down the notion of regular here, but it's really the same thing as before. You look at the stabilizer of L under the action of the Weyl group and you ask that it's trivial. Okay, so this is a definition of some character sheaves, not all. Is that is a sum of irreducible character sheaves. There are other ones as well, but I won't discuss it today. Okay, but what I was leading up to over here is that a corollary of this theorem now is that if I'm in a situation where L put back by some sigma is isomorphic to sigma, then I also have that, oops, from T to G, oh, it's isomorphic too. Over here. Okay, so I now have this object inside the derived category that has sigma invariance, and I can now run sheaf to function dictionary. I didn't require that here. Here. Oh, this one. Oh, I do. That's right. Okay. Yes, thank you. So, okay, thank you. Okay. So here's for kind of some sigma. So you like this sigma is allowed to vary. So given this picture, one should ask whether, okay, so what have we done? What we have done is we've said, okay, I want to study representations of G of FQ. One way to study, come up with these geometrically is to find some variety, take its cohomology and find representations there. The other way is to build some sheaf which one is allowed to take an associated trace of Frobenius, which gives you a class function on this G of FQ. And so how should that be related to the representations? Hopefully those are the characters of these representations from the first picture. Now, it is generally known that if you take a random summand of such a thing, then the associated trace function may not actually be the character of a representation. However, if I take this entire thing, then actually that statement is true. And so let me write down that theorem as the last thing that I will write down today. So this theorem is due to Lusztig, 1990. So, and so again, we take T inside G to be sigma stable. B can do whatever it wants. And so then the statement is like this, is that up to a constant, one knows that if you take, I guess I should write it like this. I take the trace of Frobenius associated to the geometric parabolic induction for some L theta, where L theta corresponds to an actual character theta. This is equal to the actual trace of RTG theta up to some constant. And this constant, I mean, there's some subtleties with this constant. If you want to really pin it down, then maybe you have to make some additional assumption here. And so what, i.e., these two parallel pictures give rise to the same class functions when you take the whole package of the RTG and the whole package of the parabolic induction. And so how can one think about where the subtlety is moving? Well, in the Deligne-Lusztig setting, one very major thing was this inability to form B of FQ. And that's why we had to do this fancy thing of taking this curve, right? Geometrically, you're working over FQ bar now, so there's no difficulty in choosing B of FQ bar. But where the subtlety comes in then is when you're taking trace of Frobenius, then lots of interesting things will happen. And so it's just pushing the interesting sigma part to a different part. So I'll stop here and yeah, thank you.